we'll continue testing proportions by looking deeper at the chi-square distribution and multiple proportions, in addition to what you can do if you violate the assumptions associated with the chi-square distribution. The essential questions are: what are the hypotheses for multiple proportions? What is the expected value of a cell? What is the observed value of a cell? And how do you pick the correct test when you are testing your proportions? This is our final section about the analysis of frequencies and proportions when dealing with single x and single y, or we just have two variables. Later in the semester, we will look at what to do if we have multiple predictors with a categorical outcome. That is called logistic regression. But for now, we've compared an observed proportion to a fixed standard or an historical proportion. We've compared proportions from two groups. So we collected two samples, each with a proportion of our outcome, and we've compared that proportion. Now we want to extend this to look at multiple groups and look for relationships between our two classification variables, or our x and our y. So let's have a quick review of the test statistics we've used so far, the z and the chi-square. For one proportion test, remember we're simply comparing p hat, which is our observed proportion in our single sample, to p naught, which is our null proportion. Because we're operating under the null, we use the proportion p naught in the denominator of our z-test. When we move to two proportions, rather than directly comparing p2 and p1, we created a difference and compared it to 0. And we used a pooled standard deviation, or an average standard deviation, in the denominator of our test statistic. We could also use the shortcut chi-square. So if you have a 2x2 table and you break it off into A, B, C, and D cells, you can have marginal totals and then a total n. And from there, we can calculate the chi-square method. The decision rule for all of the above is the same. We will reject H naught for small p-values. That p-value is compared to alpha. That alpha is usually 0.05. For a one-sided test, you can actually take the square root of the chi-square, and that will give you the z, and look up the p-value associated with the z-score. Or you can simply divide the p-value from jump by 2. So to repeat, half of a two-sided p-value is the one-sided p-value. So you can take the two-sided likelihood ratio chi-square test, divide that p-value by 2, and that will give you the one-sided p-value. Just make sure you know which side you're looking for. What about if we have a larger than a 2x2 table? These are also called R by S tables. Clearly, the shortcut method won't work here because we have more than 4 cells. So we have to do this the long way, quote unquote. This is what the long way looks like, but in general, it looks pretty similar to what we did with 2 proportions and 1 proportion. Remember, with 1 proportion, we were comparing what we observed, our p hat, to what we expected, our p naught, and dividing it by the variability under p naught. In this case, we're going to look at what we observed in each cell and subtract off what we would have expected to see if there's no difference, and divide it by what we expected to see under no difference. The good news is that JMP or SAS or SPSS or any statistical software that you use will do this for you. The details of this test are in your section notes. Please review them so that you have a deeper understanding of the observed minus the expected values and how your chi-square test is created. But for now, we'll move ahead. So what are our questions here? If our null hypothesis is true, that is, each of our observed values in our cells is equal to what we expected to see, then what would we think the chi-square value would equal? So if O sub I minus E sub I is 0, then no matter what we divide it by, we'll be summing up a bunch of zeros. So we would expect our chi-square value to be small. If the null hypothesis is not true, and all of or some of our observed are different from our expected, then we'll start to accumulate totals in our chi-square value that deviate from 0. So keep these things in mind, the observed and the expected values, and we'll go ahead and calculate the chi-square test statistic using our observed and expected frequencies. In the ECMO study, for participants that survived to 1 year, they were asked if their health status was better, somewhat better, about the same, somewhat worse, or worse than in the 1 year prior, compared to the 1 year prior. Table 5 shows us those results. You can see here the subset of Table 5, but we do need to adjust our N and the proportions. The ECMO group had 90 people. There were only 52 with 1 year data available. The conventional management group started out with 90. There were 33 people that survived to 1 year, but there were 2 people that did not have information for this health status variable. So we will have a total of 52 in the ECMO group and a total of 31 in this conventional group, with a total N of 83 overall. So we can take those numbers and enter them into a new Table 1, which would summarize the status at year 1 by ECMO and conventional management. So you can see here that the better now was 17.3% in the ECMO group versus 6.5% in the conventional management group, with the overall better now 13.3%. Or 8.4% thought they were somewhat better now overall. 16.9% thought they were about the same overall now compared to 1 year ago. 37.3% thought they were somewhat worse now compared to 1 year ago. And 24.1% thought they were much worse now compared to 1 year ago. So our goal here is to determine if the proportions within each row are different across the ECMO and the CM groups. That is 17.3 different from 6.5? Is 9.6 different from 6.5? Is 17.3 different from 16.1? Is 34.6 different from 41.9? And is 21.2 different from 29.0? In JMP, we can do this with the frequency table. Because we have 5 by 2, we'll have 10 rows, 5 for ECMO, 5 for CM, each with the 1 year status variables, and then of course our frequency column of N. We'd like to evaluate and describe the data, calculate the proportions of our event of interest. Well, we're no longer dealing with event, no event. In a 2 by 2 table, the epidemiological way was that the columns were the outcomes and the rows were the populations. Well, when you get into the multiple outcome situation like we have here with health status, you'll often find tables displayed in the reverse, so that our treatment groups are now the column because there's only 2 of those, and even with an overall column, there's only 3 columns. And we have 5 rows rather than trying to squeeze 5 columns into a single table. It just depends on what's natural for your data and then also what will fit in the arena that you are presenting it. So just make sure that you understand and it's clear in the presentation if you're doing rows as the outcome or columns as the outcome. We need to review the assumptions. So representativeness, independence, and sample size. So again, we've already assessed representativeness and independence here for this data set. For sample size, remember we have to look at the expected frequencies. For the 2 proportion, we needed to have an N to be large enough to expect to observe both 5 survivals and 5 non-survivals in each group. Well, in this particular case, do we have survivors and not survivors? No, we have different outcomes for this Health 1 status at 1 year. So how do we pick a null hypothesis? There are actually many ways to state the question. The basic way is that we have equal proportions across the rows by treatment group. At least one difference could be the alternative. At least one P not equal to the other P could be the alternative. Not all P equal. But really what we're testing is either equality across the rows or that there is a difference somewhere large enough for us to say that they are not all equal. And I don't mean that we've taken the overall and divided it by 10 here. We're not looking for 10% in each group in each row. We're not looking for 20% in each outcome within each treatment. What we are looking for here is the proportion of people who answered better equal for ECMO and CM, and is the proportion somewhat better equal, and is the proportion of the same equal, and is the proportion of somewhat worse equal, and is the proportion of much worse equal across ECMO and CM. The alternative being that there is a difference somewhere that is significant enough for us to say we have a difference. There are other ways toward H0 and HA. You could think about it in terms of homogeneous versus heterogeneous. Homogeneous means that things are similar. Heterogeneous means they're different. So we could be looking at our groups, our treatment groups, ECMO and CM have homogeneous responses, or do they have heterogeneous responses? We could be talking about independence versus dependence. So is the outcome dependent upon the treatment group? With treatment group as our X and outcome as our Y, are those two variables independent or are they dependent? If they were independent, we would simply use the proportion of the 1-year status as our best predictor. However, we want to know if there's a difference by treatment. We could also say there is an association between the variables versus no association. So no association here would be our null hypothesis. Association would be our alternative hypothesis. We could also talk about relationships. So our null hypothesis of the variables being not related versus our alternative of the variables being related. And our variables here are treatment group being related to our 1-year health status outcome. So back to our expected cell sizes, now that we've clarified the ways that we can express our null and alternative hypotheses. Recall the rule of 5, where in a 2x2 table, all of our expected cell sizes needed to be greater than 5. Well, the real rule of 5 is that no more than 20% of the cells may be less than 5 expected. Remember, not observed, expected. So what happens if we violate that? We could ignore it. We could collapse our cells. So we have 10 cells here. We have 5 outcomes. We could possibly collapse it to be 3 outcomes or 2 outcomes. And collapse means to merge or add together some of the groups. For example, we could collapse better and somewhat better into one group, or worse and somewhat worse into one group. We could do no change or better into one group and worse as another group. So we could go down to 3 groups or 2 groups if we wanted to collapse cells. Or we could use more complex statistical methods. So how do we check if we need to do more complex or collapsing? Well, the good news is that JMP will do this. Again, remember, we have an average proportion for better, somewhat better, same, somewhat worse, and worse. And what we would do is take that average proportion and multiply it by the n in each group, and that will get us our expected value. But JMP will do this for you. Fit x by y, or fit y by x. Use the red arrow next to contingency table and ask for expected. We'll see how to do this exactly or precisely in the JMP video. But for now, here's the output. And what you can see is that the CM better group has an expected of 4. Uh-oh, that's already 1 cell that's less than 5 expected. Right next to it, we have a 2.6. That's another cell that's less than 5. Continuing on in the CM group, we see the remainder of our expecteds are greater than 5. And in the ECMO group, we see they're all greater than 5 except the somewhat better. So we have 3 cells here with an expected count less than 5. So we're in trouble because 3 cells out of 10 is 30% of cells, and that's more than 20%. So our rule is violated. So we cannot use our large sample chi-square test here. So what do we do? Again, we could ignore the possibility of a problem. We could collapse the cells, or we could use more complex statistical methods. We'll actually look at all 3 ways. Let's start with number 1. Why is this a bad idea? Well, you actually know it's bad because you know that we cannot rely on a large sample test. We don't have the sample size that we expected to need to rely on a chi-square test. And in fact, JMP tells you you can't do this. If you look down at the bottom of your fit y by x output in JMP, you will get a warning. 20% of cells have expected count less than 5. Your chi-square results are suspect. If your software is telling you that you can't use these results, then you should believe it. No matter how much you like the results here, they are not correct. So we need to ignore these fit y by x results and move on to option 2 or 3. In our case, we have several options for collapsing cells. They need to make sense in the way that you collapse them, though. So we wouldn't want to collapse better and worse into the same category because they're on opposite ends of our spectrum here. We wouldn't want to collapse somewhat worse with better or somewhat better with worse. We really have the option to make somewhat better and better a single better category, and make somewhat worse and worse a single worse category. That will give us 3 levels: better, the same, or worse. You could also potentially collapse this into 2 categories. So you could do worse versus the same and better, or you could do better versus the same and worse. It really, you have to think about what is meaningful for your outcome. In our case, we're going to do 3 categories. So we have a new data and a new data table in JMP. So you can see here that we've collapsed the better from somewhat better and better now into one. The same is still its original category, and then we have the worse collapsed together. Here are our expected cell counts based on that. We can see that we expect greater than 5 in all of our cells, so we're okay to proceed here with a chi-square test. We'll go back to our summary statistic. You could calculate your observed versus expected utilizing these numbers, observed versus expected, square the difference, divide it by the expected, and sum them all up. But it turns out JMP will do that for you. How could random variation affect the statistic? Well, if our assumptions are met, which they are now, we know that our chi-square will have a chi-square distribution. If HO is not true, then differences will yield a chi-square value that's much larger than 0. Here's what the chi-square distribution looks like. It actually depends upon the degrees of freedom. It will change shape based on the number of rows and columns you have. In our case, we have a degree of freedom of 2. You can check the notes for how the degrees of freedom are calculated. But what you can see here is that the larger the degrees of freedom, the more normal or bell-shaped this begins to look. Even by 8 degrees of freedom, we're relying on large sample normal statistics. It doesn't actually matter. You don't need to be able to find the critical values here from tables. Remember, the area under each curve is always 1. And because we know that, we can find out where our chi-square statistic is, and that will give us a p-value, or the probability out of 1 that has the same exact interpretation as a z-statistic. Stated decision rule, it doesn't change. It will not change throughout the course of this semester or next semester or the rest of your statistical career. When you're using p-values to make a determination between H0 and HA, we will reject the null hypothesis with small p-values. Calculate the test statistic. So we'll use fit y by x in JMP. Put status as the y. It was measured after our treatment assignment. We'll put treatment as the X. It's our predictor variable. And then make sure you've pre-selected N as the frequency, or put N in the frequency in the fit Y by X window. We're going to use the likelihood ratio test statistic here. You could use the Pearson, but the likelihood ratio test statistic has been shown to be a more robust statistic. That is, it withstands departures from our assumptions better than the Pearson chi-square does. So just make sure that you use the likelihood ratio test statistic. If you use the Pearson, state it's the Pearson. Using the likelihood ratio, state the likelihood ratio in your methods. When you write these up for journals or for results for meetings or for grants, just make sure you specify which test statistic you use. We'll use likelihood ratio test statistics in this class. Then make a statistical decision based on your p-value. Is our p-value less than 0.05? No, it is not. It's actually 5 times that, so we will fail to reject the null hypothesis. State our substantive conclusion. We fail to reject the null hypothesis and conclude that the health status at 1 year is not different by treatment received. The caveat here, of course, being you need to condition on the fact that this is for people who survived to at least 1 year. So those that died prior to 6 months would have no chance of being included in this data set. And that is something that you need to be careful about writing in your descriptions. And that goes back to conditional probabilities. We have conditioned on the fact that people survived to 1 year. If they survived to 1 year and answered the health status question, they have been included in this data. From this data, we have concluded that the health status at 1 year is not different by treatment received. You would then want to document your complete understanding, including the conditional nature of our data. So a sample of 180 ARDS patients were treated with ECMO or conventional management. At 1 year follow-up, 83 provided or had information regarding their health compared to the prior year. And then include the information on how that was measured and reference Table 1. Health status at 1 year was not statistically significantly related to treatment group. And here are our chi-square and our degrees of freedom with our rounded off p-value. Some journals will specify how many decimal places you have for your p-value. Usually for non-significant p-values, it's 2 decimal places. Make sure when you're making your notes to keep all 4 decimal places so that you never have to go back and refit your models. You'll always have your full documentation and you can round up or down as needed. So how do you write this up in terms of the proportions? There are a lot of ways to explain your results, particularly if you do find something statistically significant. So you could think about row proportions, column proportions, or whole table proportions. Choose only one of them. JMP will give you all 3. Whole table proportions would be the cell n divided by the total n. This is actually relatively rare to write up because you would be talking about the n in ECMO that were better out of all of the patients that you observed. And you really know that you want to be talking about the percentage of better by ECMO or by CM. So you could then look at row proportions, which would be the number in the cell out of the number from the row, or column proportions, which is the number in the cell divided by n in the column. This, of course, depends upon what are your rows and what are your columns. Just make sure that you pick only one so that you have either all row proportions or all column proportions in your table, and you're consistent in how you refer to them in your description. Choose one approach, whichever seems most natural. In the case where you do have intervention groups or 2 different samples like ECMO and CM, you could have an exercise intervention versus a diet intervention. In those cases, you'll want to be talking in terms of proportion out of that treatment group. It could be proportion out of a race. It could be proportion out of a gender. It wouldn't make much sense to talk about the better responses out of better, which percent were in ECMO and which percent were in TM or CM, because those were assigned. The treatment groups were assigned. So if you have a natural conditional group, then do the proportions out of that. Up next, we'll continue this example if we didn't want to collapse our cells and wanted to use the Fisher's exact test.